Hello, this is an updated tutorial on the use of the Dimensionality Reduction plugin for ImageJ of Fiji version 1.0.6. Jumping straight in, this is the Olivetti face data, which I think I used in the last tutorial as well. A stack, 400 images, 10 images from 40 people, face data. As before, we can run the tool from the GUI dropdown. So we'll just show you some of the newer features of the PCA component. So as before, we get a dialog open, but now we've got a few more options than the last video tutorial showed. We can choose to suppress the normal ImageJ plot. We can create the FX plot, so the Java FX interactive plot as before, but there's a few new features included in that plotting as well. As before, we can label the points of the plot based on some ground truth state. So in this case, we'll take it and then choose maybe a file corresponding to the order of the images. So I'd being able to label each individual in that plot. We now have the option to also output eigenvectors or eigenfaces, I guess, in this case. This dialog sort of window or input box allows us to select multiple eigenfaces to display or eigenvector to display, separated by commas and also including hyphens for ranges. So for instance, we can output the first 50 eigenfaces here. The components to use, so the number of principal components to compute should automatically be updated based on the higher number here. I'll just put it 51 to be on the safe side. And then we also have the option to output the mean image. So this is the average of all the faces. It's actually a metric used within the component algorithm, but it's a nice sort of output image as well. So if we click OK, because I asked the plugin to use a ground truth condition to color the points, it's now asking me for that file. And as before, we have the face labels. So I think I can open this just to show you what this looks like. It's just a single column with one header. And these are sequential, but that's just because the order of the images is sequential. It doesn't matter that they're in order per se, as long as this order reflects the order of the images in the stack. So we'll highlight that, click OK. It's asking me if I want to process the stack, so I'll say yes. We have a log output here that I'll go through in a moment as well. So this is a PCA output. So this is the traditional normal ImageJ plot, which isn't interactive, but comes with all the features built into Fiji and ImageJ. I'll just close that for now. Here we have the mean image that we requested. So it looks a bit ghostly, but that's, the nature of, because these are standardized and normalized images, they're all in roughly the same position. The mean image kind of captures the orientation and the overall kind of composition of this framing. Now the eigenvectors, this is even more ghostly. This engenders some information naturally with respect to this data set. It isn't always going to be so sort of naturally or we aren't always going to be able to intuit the meaning of these, but for face data, it has sort of a natural representation. The interactive scatter plot, as before, generated. These are colored by ground truth state. We can see that some faces cluster nicely together. So number 22 here, I would just toggle on and off using the interactive plot. And PCA is not the best at clustering these, but clusters do broadly fall within certain zones. Now, we can also click on any of these to highlight the underlying image in the data set. So we can see it's automatically updating here. A nice feature of this plot and this version of the Dimensionality Reduction plugin is that we can left click and highlight zones. We'll automatically enumerate the number of points in that area. And whilst we're on the log window, actually, after PCA run, we've also got eigenvalues represented and the percentage of variation captured within each principal component range. So I think in other tools, this is described variance. So we can see that principal component 1 explains 21.26% of the total variance, PC2, 14.63, and then after that point, so PC1 and 2 is just the default output. We could have displayed on the chart principal component 7 and 11 if we really wanted to, or any number. And then those would be described in here and here. However, the software will also just output many principal component ranges after this as well. So we can see the first 100 principal components describe 93% of the total data. Right? And from this zone that we drew, this region of interest, we can right click it and ask the software, just make sure that's selected, ask the software to output the images that correspond to these points. And it'll create a substack, which we got here, which is a substack of all of those images just from that zone, which is a nice feature. And you can see that in the plot here as well, the number in parentheses corresponds to the position in the original stack. Yep, so we can see that number 7 here is indeed that image. As before, if we right click the plot, we can copy a static image of whatever is presented on screen to the clipboard. We can save the interactive plot as before and then reload it and be able to still interact with it in similar ways. And then a new feature of this version of the plugin is that we can also recolor the plot. So we colored it originally by specifying a label file. We can also recolor it by principal component. Now, this doesn't just apply to the PCA dimensionality reduction function of this dimensionality reduction ImageJ plugin, but you can actually recolor by principal component for both t-SNE and UMAP as well. However, we can do this here. And for instance, we already know that principal component 1 is represented on the x-axis here, but let's recolor all the points by principal component 1. So there we go. Because it's already computed it, it was instant. And this is reassuring, right? We can see that the color gradient goes from black to red. It's in the current version, I've just set it to a single color gradient, always black to red, and it automatically determines the dynamic range from the maximum intensity on an 8-bit scale to the minimum intensity on an 8-bit scale, irrespective of the absolute values originally. So obviously the absolute values here is 0.1 to 0.1 minus 0.15, but this is scaled it from 0 to 255, which is the 8-bit range. It doesn't just have to be the principal component that we've already got there. So we could recolor by principal component and pick 3, right? And now suddenly we've got a 3, almost like a 3D representation, right? Because we've got principal component 1 on the x-axis, principal component 2 on the y-axis, and then principal component 3 represented as the color differential here. And we can keep going, right? We can obviously go to like principal component 4, etc. If we can restore, once that's been recolored, we can then restore the color back to whatever it was originally. And you can see that's only highlighted if we've tried to change it here. We can also recolor by input variable. So in the case of images, the dimensions are actually the pixels. So if we know a pixel, let's say, or dimension that is interesting for us to map as colors to the original set. For instance, we might say that, I don't know, like somewhere in the middle defines something meaningful, right? Although there's probably a little bit less variance there across the whole image set. We can do something like that. Right? So we can pick a number. So the way the pixels are fed into the plugin here are row by row. So we could probably do something like, I mean, this is probably not strictly necessary to show you this right now, but we could pick something like 64 times 64, which is the pixel, the total number of pixels in this image, and then divide that by 2, and pick somewhere in that range, right? So let's pick 2000, or 2020, or 2048, right? So we can recolor this by input variable and pick 2000 and 25, say somewhere in the middle. And you can see that now it's recolored them by that, you know, so whatever variable is there. Now, this probably is more meaningful for when you're processing other modalities of data, right? So for instance, if you're processing gene array data, where you have tens of thousands of genes, you could then recolor the PCA or the t-SNE or the UMAP plot by a single gene's value across the whole data set. So that's showing you some of the main features of version 1.06. However, I'll show you on its different data set now, just to show you that it's robust and maybe also employ a different tool than PCA. Oh, I probably didn't have to close the Fiji there, so I'll just reopen it. And we'll open, let's say, the a rotating set of letters. So I have here, it's one of my favorite sets to test dimensionality reduction on. It's a bit artificial. So we have 3 letters, A, B, and C, that rotate by 1 degree each time in a data stack, an image data stack. And now we can run UMAP on it. So I think this example might have also been included in the last video tutorial, YouTube. We don't have to change too many of these parameters. So I'll just put something like 50 here. Yeah, we can label them by ground truth state again, why not? And create the interactive plot. We'll pick the ABC labels, which is similarly orientated as a single column, single headed column. Yes, please, let's process the stack. Okay, so here you go. Again, the original ImageJ plot, which we can choose to use if we want, but the interactive plot is the one we'll focus on for the moment, because this engenders many of the new changes in the DimRed plugins version 1.06. So here, as before, we can highlight the different points. So we can zoom in with the mouse wheel, double click the plot window to go back to the original zoom. Obviously toggle the states as before. And here I'll give you the example of running or recoloring by principal component, even though we didn't run PCA originally. So let's recolor by principal component 1. Now we're going to get a little window here saying that it's being computed, because this time it has to compute it for the first time for this data set. And it's done. That can take quite a while for very large data sets, especially where you have a high number of dimensions and a high number of samples. But this is interesting, right? Because we can see that principal component 1 has done a very is very good at defining A relative to B and C. Now it's been computed once. It doesn't have to be recomputed every time. So this time we can color by principal component 2. You can see how that's represented naturally on the plot here as well. As before, we can highlight one of the regions, let's say A, highlight the whole cluster, get it enumerated, output it to stack, and just to show that it's actually working, yeah, there we go, all the A's. And then finally, I'll run the tool on a table, because in the last version, there was a way of doing this, but it involved collapsing or transforming the table into a stack first, which is not now required. So this version of the plugin can be run directly on the table. So we can see here the traditional iris dataset, machine learning dataset, which constitutes 150, I believe, samples of flowers, around 50 of each group of 3 species, and then 4 variables. So not many dimensions to reduce in this case, just 4. But this is just an example anyway. So let's run, for instance, UMAP again on this one. I mean, we could for argument's sake do like t-SNE at this point, right? But let's do UMAP. Let's not worry too much about all these. And I could label them by their data points, but let's just for argument's sake leave that off for this example. Do I want to process a table this time? Yes, please. So here we go. So this is the UMAP representation of the 3 colors here. Now, of the 3 flower types. If I'd have chosen to color them a ground truth, you'd see there's actually 2 clusters that sort of next to each other here, but that were sort of visually distinct. But certainly at least one of the groups has separated as a separate cluster here. And as before, we can recolor this. So this time, let's recolor them by input variable, right? Which makes a lot of sense for tables. So we have column 1, 2, 3, and 4. So we can color it by sepal width by selecting 1 here. And that's what it looks like when you recolor by sepal width. We do another one. So recolor by, sepal length, right? Let's recolor by sepal width this time. And there we go. That's what it looks like, recoloring by sepal width. Basically, that's capturing most of the new features, if not all of the new features of the new version of the Dimensionality Reduction plugin, which is available to download via the links in the description. And there should be also a link to the GitHub page describing this tool. So thank you very much for listening.